right? So how do we handle these errors? A classical way of doing that is by using if statements, right? So what you could do is you could just say, well, if you expect invalid inputs, so for instance, we want to divide by a number, and there might be the case that x is equal to 0, then of course we could just check that case, and we say if x is not equal to 0, then we can execute the statement, and otherwise we put an error message. The problem with that is that there might be a lot of different cases that we don't really think about. Essentially, for every line of code, right, we would have to think exactly which cases might happen. Have I catched all of them in the if statement? Have I handled them all in the if statements? And then our code becomes very, very convoluted because of that. So every line, potentially unsafe line of code needs to be kind of wrapped along many, many if statements.
It also becomes hard to read when it's cluttered with all.
It becomes very cluttered.
Texts everywhere.
Yeah. So Python uses a strategy called exception-based error handling. And essentially, the way this works is that statements, any code statement can potentially throw a so-called exception. If something goes wrong, it throws an exception. And you, as a user, you have the possibility to handle that exception or just ignore that exception. And if it's ignored, then it will be passed over. And if no one handles that exception, then the program crashes. So if you have a potential problematic statement, and you want to handle the exception that might occur, you use this syntax here. You have a try statement, and in the try statement, you put in all in the try block, you put all the statements that are potentially dangerous, right? So essentially, you're trying out to execute that code. So here you might want to divide by 0, or you want to divide numbers, or maybe you want to open files, and so on and so forth. Then you have an except block. This block is only being executed if something goes wrong in the try block. Okay? So if an exception occurs here, or if an error occurs here, then we will go into that part of the block, and here you can handle that case. Right? So maybe you want to put an error message, but maybe you just want to ignore it or do something else. And then we have a finally block. In this code here, this is optional, and this is always executed independently of what happened before, right? So either the try program here was running fine, then we will still execute finally. But even if we hit an exception, that you will still hit execute the finally. The reason why we have that is because imagine in your try statement you're opening up a long file or maybe a database, and you're doing some database operations here, and something in between, something goes wrong. So you hit the except block. Then you still want to, at the end, you always want to make sure that you close the database correctly, no matter if the command was successful or not successful. You always need to make sure that your database is being closed correctly. And the same thing happens often if you work with files, right? At the end, you always want to close the file, no matter if the file operation was successful or not. So here's a very simple example on how this might look in practice. So our potential dangerous operation is shown here, and I've wrapped it in a try statement. I say print 1 over float of x. So I'm trying to convert something, my input, into a float, and then I divide it. I use it as 1 over. And of course, there's many ways how this can go wrong. So I put in a try block, and I have an except statement. In the except statement, I just write print invalid division. And then I also have a finally block, which we should always see. So now we can test this out. So of course, maybe the first thing that we should do is we put something valid in here. So I use x equals 1. And so I execute this, and our output is 1.0. So 1 divided by 1 is 1. We don't see that statement here because everything has gone fine. But we always see this statement because it's in the finally block. So now what we can do is I can put in a 0. And now you can see that this statement here failed. We hit the except statement, so we see this error message invalid division, but we also see the error message in the final block. So the interesting part here is that now our program did not fail anymore, right? It executed just fine. And you could have, I could have continued here and say print hello. And it will execute just fine. Because we're handling this error, and what before crashed now is handled fine, and the program continues to run. And of course now there's also, I could put in a, not even a number, so the conversion to float might fail here. But so if I put a here, then converting a to float will raise an exception. But again, this will be handled just fine. So essentially, this except block here handles any possible exception that might occur, any possible error that might occur in the try statement. So sometimes it's useful to get access to the actual error message that occurred. And you can do that by getting a handle on the exception that occurred. So here, the way you do that is you just write exception as E, and then you have this object E that you can, for instance, print. And then you get a more detailed error message. So if I execute this, A was a string here, right? And now you see invalid division could not convert string to float A. This is the printing out the exception as a string. Gives us the error message. And then, of course, if I put in a 0 here, and execute this again, now you get the error message float division by 0. So then, sometimes it's useful to test for specific division, for specific exception. So maybe we know how to handle division by 0, but we don't know how to handle the case where we need to convert a character to a float. So the way you do that is you say except, and now you not only specify exception before was kind of is the mother class. So any exception is, any possible error is always an exception. But if you're being more specific here, then we only handle, in this case here, the 0 division error. So this block, this code example here will handle the 0 division error, but it will not handle the, what was it? I'm not even, can't remember, but we can test it out now. So the point here is if I put in a 0 here now, that works just fine and we're handling the 0 division error. But now if I put in an A here, this becomes a value error. So trying to convert a string into a float, A into float, raises a value error. And we're not handling that because we haven't listed it up here. And so hence the program crashes. So if I wanted to handle it separately, I could have a second except statement here. And I could say value error. And I then print, I handle this also. Okay? And so now you handle 0 division error with that in this way and the value error in this way. And so if you're interested in all kind of possible different errors that might occur, I use this IPython magic here to list all of them, and you can see there's a lot of different errors that you can that might potentially happen.
You can create your own.
Yes, we come to that in a second. So you can even create your own ones, but before I show you that, I want to show you that you can also raise your own exceptions, right? So, of course, you need to know how to handle some, but sometimes in your program, you come to a point where an error has clearly occurred, you don't know how to handle it, so then you want to raise an exception. And the way you do that is you use the keyword raise, then the error that you want to have to raise, maybe you're hitting an index error, and then you can provide a message. So a very simple way of doing that is, a use case of that is, for instance, if you wanted to, sometimes it's quite useful if you have a function and you want to handle a certain exception, so for instance, zero division error, but you don't like the error message that comes out of the zero division error, and you just want to change it. And so then what you do is you have a try block, and then you have an except block, where you catch the zero division error, and then you just raise the same error again, but this time with a more concrete error message. So type of E just becomes zero division error. I could have also written zero division error here. And then this is my more detailed error message that I want to provide to the user. So essentially I want to have more customized error messages. And so, for instance, now if I call double invert 1.1, then everything works fine. But you can see this function here, if you plug in a 1 here, then you get 1 divided by 1 minus 1, which is going to fail. And the same here, I have x plus 1. So if you have x equals minus 1, it will also fail. But the point now is if I call double invert 1, now you get a much more customized error function, right? Input arguments to double invert may not be 1 or minus 1, while before you only got division by 0. So for instance, just to give you an example, you can use this to customize your error messages. And then at the end, you can also create your own exceptions. The way you do that is you create a class that derives from base exception. And that class is really the only thing that it needs to do, well, apart from deriving from base exception, is that you might want to implement the string method that returns a nice error message. So once you've defined that new type of error, custom type of error, you can call raise my error. So, I mean, you can also catch it. Do this. Now we have our own custom my error here. Okay, so I want to show you now in our implementation of the Monty Hall game what I've done. I mean, that was the entire purpose, right? We wanted to make our Monty Hall game more robust. So what I've done is I've created a new invalid game input exception, which you can see here. So it's just a simple class that derives from, actually should derive from exception. And so all I do here is it's essentially an empty class with the string method. And so now, in the game logic, what I do is, whenever something is, let's see where something can go wrong. I think I need to go in here. Nope. Oh, yeah. There we go. So in my game logic, whenever the user provides an invalid input, for instance, if I try to select a door that is outside the range 1 and 3, right? It doesn't make we can only open doors 1, 2, or 3. So if the user provides an invalid door, I raise an invalid game input and provide a nice error message. Door must be an integer between 1 and 3, and you provided this number. Right? And the same thing is if the user tries to open a door that is already opened. Right? If the TV moderator opened door number 2, and in your second try you say, I want to open door number 2. Right? So that is invalid. So I again raise an invalid game input here. So essentially my game logic can raise various types of errors depending on the inputs that the user provides. And then in the actual user code, so if you look at the command line interface here, so here I've done, I kept it very, very simple. So essentially what I do, so remember this command line interface was a big loop where every time, in every loop iteration, I played one game. And essentially what I've done is I wrapped this entire loop here into a try statement. And I know that maybe in between, in any of these commands, the user might provide an invalid door. But if he or she does that, what I do is I just catch that error. So I have an accept invalid game input. And I print the error message and just restart the game again. So I just say, OK, this game is clearly invalid. I just discard it. And I start from scratch again. And so now, if you try this out, okay, so now I selected door number between 1 and 3. So if I select a valid one, that's fine. But now if I make a mistake here, I get my invalid input game input exception. Door must be an integer between 1 and 3. You provided 5. And just restarting game. And things start again. So now we kind of have a more robust implementation, but before it would have just crashed. All right. Next, so that was error handling. Next thing that we need to learn is how to add tests. So you already know how to do that. Where we use the PyTest module. What I typically do is in my packages, I create a new subfolder called tests. And then in there, I just list all my tests for each separate module. So I have test underscore module name. And then in that module name, I list all the tests. And all right, maybe just another tip here is the naming of the tests. They should be quite, in every test is essentially a function, and you can freely choose the name of the function. And it really makes sense to give them a descriptive name. So what I typically do is, the name always have to start with test, and then I really describe in words what the test does. So for instance here, the test could be called test that game wins or loses. Right? And essentially what I do at the end is I have assert one or not one, so that they can't be kind of any, there's no draw essentially. Or here I test that selecting invalid door raises exception. Right? And so I actually make a try statement where I put an invalid error in here, and I make sure that an exception occurs. And in that case, I continue, but if no exception occurs, I actually I say assert false, which will raise an exception, and then the test will fail. So kind of I check that exceptions happen, essentially. But the point why it's quite useful to have good names is because when you run a PyTest with a -v flag, you can see the name of the tests. And then it becomes really, really important that you kind of just by reading, maybe one of them failed, and you get a very clear idea on which one failed if you have good names. So one tip here that I also want to mention is, just like the documentation can be automatically compiled when you push your changes to GitHub. You can also, GitHub can automatically run all your tests when you push to GitHub. So the idea is that your GitHub repository is kind of the holy repository, and that should always be working. And the way you check that is by constantly running tests on your GitHub repository. So there's GitHub, there's this Circle CI service essentially that provides the automated testing for your GitHub repositories. I can show you how this works for one of my projects. This is not, in this case, it's Bitbucket, which is almost like GitHub. Doesn't really matter. But the point here is, here's my commits, the list of commits that you can see when you're on the website. And then here on the right-hand side, these are the automated testing that have been performed. So whenever someone made a new commit, the test was run, and when it's green, then all the tests have passed, right? So then I'm happy. And actually, if it fails, then I normally get an email even. So you see down here, something failed. But I can click on this. And so now I get to this integrated testing service. And I mean, there's a lot of, it needs to kind of install the environment and do loads and loads of stuff. But down here, you can see run tests. If I click on this, right, you see essentially the, you can see it executes Python 3 -m tests -v and then my test directory. And here you can see all the tests that have been executed. And of course, one of them might now be red, and then depending on the name, I can immediately identify what might have gone wrong. No, so this is when there's an X fail. This is actually an expected failure. So sometimes you have tests where you know that they should fail. Right, so now the next step to get to our project is to have a setup.py file. You're already familiar with that. So in your main directory, what you add the setup.py file where you specify which packages should be installed and the package name and so on and so forth. The only comment that I want to make here is that I also have this scripts argument here where I specify the executable commands. So both the bin, play, Monty Hall command line interface, but also the web interface are scripts that should be installed. So after installing that package, these will be available as directly as commands in the command line interface. And then, of course, you can use Python 3 setup.install, but you can also do pip3 install dot to install your package. If you do that, the nice thing is you can also uninstall it again. You can write pip3 uninstall Monty Hall again. And I mean, these are now really trivial things. So of course, it's useful to have also installation instructions. So it's common to have a install file in your project that describes how you install your package. So in this case, I added this requirements file, requirements.txt file. That's simply a file that lists all the packages that my project depends on. So in this case, it would be Flask. We can have a look at it. I thought I already had that. So requirements.txt is simply a file that lists all the dependencies. So in this case, I depend on Flask, PyTest, and Sphinx. That should be installed. And by the way, they're also used then for the automated testing environment, so that because that also needs to know what needs to be installed in order to run the tests. Yes, and so now if we look at the final project layout, right, our project has grown quite significantly. We now have a main project folder, then we have our install file, we have the requirement file that lists the dependencies, we have the setup file that describes how to install that project. We have now the Monty Hall game. This is the main module. We have our init file. Then we have the game exceptions. These are my custom exceptions that I've coded up. Then Monty Hall game module that implements the core logic, game logic. Then I have a bin folder where I have both the command line interface and the web interface and also the templates in this case. Then I have the documentation folder. This is fairly empty for now. Well, it only contains kind of the core files. But as soon as I type in make HTML, of course, there's a lot, this _build folder contains a lot more files that are automatically generated. And then I also have a test folder. And so that structure you will see in a lot of larger open source projects. Any comments so far? Yeah.
If you have the documentation and you want to have it both in text format and in HTML, then you probably would want to have subdirectories on the doc. One HTML, one PDF, and so on.
Yeah, but so remember that these are generated. So in your repository, you don't commit any of the HTML files and none of the PDF files, because you only commit kind of the raw rich text format files. And so the PDF files and the HTML files, they're automatically generated. And so typically I let read the docs generate them for me.
Yeah, but when
and so
you
read the docs.
them, won't you then generate them into a separate folder so that the HTML and text files are not
Right.
mixed in the same directory?
Yeah, I mean, that's up to you.
Yeah.
Any other comments? Okay, then I want to teach you one last thing in Python today. It's called decorators. So decorators, we've seen, this is kind of an advanced Python functionality that you've already used, but I've never explained what it is. So decorators are these funny and then some name here that you put in before a function. And you've already used that, right? So when we used this just-in-time compilation, we decorated a function by adding this @chit in front of it. And we also used it when we did when we vectorized function in NumPy, and when you used Flask to specify which route the Flask router should listen to. So these things here are called decorators, and I want to explain to you what they do. And I will prepare you very, very slowly, step by step, towards them. So we will start by reminding you that in Python we can have functions as arguments. So this exemplifies this. Here we have one function, an add function, that simply adds two numbers, and then I have another function that just subtracts two numbers. And the idea now is I have an apply function that takes as input one of these and executes that function on the values x and y. And so, of course, I mean, the syntax is fairly simple. So apply takes in the function itself, and then the x value and the y value, and then it returns simply the function applied to x and y. And that works as expected. So then you can do apply add 1, 2, and you get as a result 3. But you can also call apply sub 7, 5, and then you get the sub 7 minus 5, which is 2. Okay? So this is functions arguments. We can also nest functions. We can have function inside functions. So here I have a function g, and inside that function I define a new function cube that takes an x, and then it returns x to the power of cube. right? And so the function g, what it does, it returns y times the cube of x. And so here the interesting part, right, is inside the function definition, I create, or when calling g, I on the fly create a new function cube and execute it. So we can even go one step further and say, well, maybe we can create a function that actually returns functions. And this is exemplified here. So let's say we have a function h, and inside that function we define a new function called inner h, and we simply return that function. And so the reason why you might want to do this is because you might want to customize it. So maybe pi here, this is just a constant, but it might also come in as a parameter. And then inside the function diff inner h, you can see depends on pi. Okay? So this h function essentially generates a new function and then returns it. So then now what we can do is I can call h. H returns an object foo, and if I check the type of foo, it is a function. And then I can call foo, and I get inside inner h, but I can access pi equals 1.13, right? So which is exactly the implementation up here. So it's interesting, right? Because this value pi hasn't really it's defined outside the function definition, but it's here it's still in the scope. If I call foo here, the value 0.13 is still in the scope when calling. But now we are very close to creating our decorators, because essentially decorators are nothing else but functions that return functions. So here's a very, very first simple decorator. It's a toy example. So we have a function foo that simply returns 1. And now we create a decorator function that takes a function as an input and defines a new function that wraps the original function around it. So essentially we have outer that takes in func, and then inside outer we define inner, and inner does something. For instance, it prints before calling func, and then it returns, and then it executes the original function. So this inner now is a decorated version of the original function. See, it calls the original function, but it also does something in addition. It does this before calling func print statement. And now it's this decorated inner function that we return. So why would you want to do that? It's because, so now what we can do is we can take our original function and call the decorator on it. So we can call outer of foo, and then what we get is a decorated version of foo. Okay? And if I call this decorated version of foo, so if I just call foo, I just get 1. But if I call the decorated version of foo, I get a print statement before calling func and a 1. So I've wrapped my original function inside the decorator to make its behavior change a little bit. So to give you a bit more concrete example, imagine you have this function f that computes log of x minus 2. And so this function is, that's fairly simple and it works well. So for instance, if I call f of 5, then I get a nice value. But if I call f of minus 1, I get a value error. And so now what I want to do is I want to use a decorator that to change this behavior of f so that it only works on valid values of inputs. And so what I do is I define a decorator, which I now call checkRange. checkRange takes in my original function And then inside the decorator, I define a new function that that is safe with regards to the limits. Okay, so my new function takes in x. Actually, this limit we can just forget about. It doesn't matter. Okay, so my new function also takes in x, just like the original one. Here, f of f took also an x, so my decorated function will also take an x. And if I check if x is smaller than 0, then I just print out of range. And otherwise, I execute the function that was passed in. And so then I return the decorated version. And so see what I can do now is I can now call check range of f. So I apply the decorator to the function f, and I get a new function out, fcheck, which is my decorated version of it. And now, this decorated version behaves just like the original one. So if I call f of 5, I get minus 0.39, which is exactly the same as above here. But now if I also apply it on minus 1, I get this error message instead of the crash that I got before. So this is the decorated version. And things now becomes, so once you've defined this function, you can decorate this function now much more elegantly by just writing @checkRange in front of the function definition. And so now, before it was called f, now I have a new function called g that I also want to decorate. And so I simply implement the original function, and then I add this @checkRange, and automatically my function is being decorated using the checkRange function. So now, if I try to execute g of 0, I get out of range. If I remove this decorator, I get a crash. Okay? So now I want to show you a really cool example of this decoration. It's a concept called memorization. And it's quite fascinating. The idea is very simple, but it's very useful in some circumstances. Imagine you have a function that is really slow. Here I just called it slow. And it's actually not very slow because it just multiplies two numbers, but I simulate it to be being very slow by adding a sleep statement. So the sleep just sleeps for 1 second. So essentially here we have a very, very slow function. And I can also, we can time it. And so hopefully it should take about 1 second. Right? Yeah, so one second per loop. But now the idea is that, so imagine this is a very, very complicated computation that is happening in here. Now the point is that maybe we call this function with the same inputs over and over again. And so we essentially do the same computations over and over again. Wouldn't it make much more sense to kind of cache which inputs have been provided and so the inputs that have been calculated together with the outputs? And if the user calls the same function with the same inputs again, then we just use the cache to return the outputs rather than doing all the computations again. Okay, this is the idea of memorization. We remember all the inputs and the outputs of a function statements, and if we use the same inputs again, then we just use the cache rather than calling the original functions. And this is a prime example for using a decorator. And here's an implementation of how this decorator might look like. So I call it memorize, and it takes a function that I want to buffer or to memorize. And essentially, the idea is fairly simple. So I have a cache, which is just a dictionary that remembers the function inputs and as a key, and then the value is the function output. So my decorated version of the function takes in x and y, just like the original one, and I check if x and y is in my cache, then I just return the value of the cache. And otherwise, I execute that function. Right? So here, this is the potentially expensive step. So here I have to call the function, I have to do the expensive operations. I store the results, I add the results to the cache, and I return the results. So this is my decorated version of the original functions, and then I just return inner. Okay, so now I can take my original functions, slow function, and I simply add this add memorize. Right? I mean, maybe memorize can now be in a different module, so we just import it. So I can write from memorize import memorize, and then I can go ahead in my code and just write, take my slow function and add this add memorize value in here. And the implementation is exactly the same. And so now this becomes exciting. So now I execute it for the first time, and you will see this, the first time should take roughly a second. Okay, now, okay, that took roughly a second. But now it's in our cache, right? So now if I execute it again, it's instant. And of course, if I now change the input values, 1, 4, then it should take again a second. And so not surprisingly now, if I time this, this is now incredibly fast, right? Because I'm just relying on the cache. So now I'm down to 304 nanoseconds per loop. So, of course, this is kind of a trivial example, but if we look, so if I so the problem with this memorization at the moment here is that it assumes that our input takes exactly 2 arguments. But maybe sometimes we want to memorize functions that have just 1 argument or n arguments. And the way you can do that is in Python, you can use this star argument to say, and then the variable name, and just say, okay, I want to have all the parameters that are in here, so the list of parameters, just stored in args. So args is now a list of all the parameters. And so now I can generalize this here as well. So I can just say if args is in cache, so just replace all these x and y with args. And here I use the same star operator to delist it. So now I provide all the values of args as arguments to the function. And I use args here again. So now I've just rewritten this quickly so that we can, now I remove this assumption that our original function just takes 2 arguments. But this memorizer will now work for any arbitrary number of parameters. And so now we can test our memorization of on the Fibonacci function. The Fibonacci function is a recursive, here I have a recursive implementation of the Fibonacci number. And so it just takes a single value n, and then you want to compute that value. And so you can see it uses fib of n-1 and fib of n-2. And so this is being recursively called. And if you're trying to, so I've tested this a little bit, 35 is the absolute highest number that I can compute. On 36, it takes forever. But 35, with this implementation, I still manage. So it takes a few seconds. Okay, so it took roughly 5 seconds to compute this Fibonacci number for 35. But now the point is that if you think about this carefully, you see that we always call fib of n-1 and n-2. So essentially, we will recursively, so there's a lot of calls that are actually being duplicated. So this is a prime example of memorizing the Fibonacci function. So if I now add my decorator here, and I redefine that function in a decorated manner, and I now execute this, we now reduce the runtime from 5 seconds to roughly, right, okay, so it's actually, right, we should maybe just call it, because this is decorated, so this will be skewed. Oh yeah, but this is now in the cache. Oof. Can we empty the cache? Okay, I empty the cache again. There we go. Oh yeah, but it's almost instant. Okay. So we went kind of from 5 seconds to an almost instant computation thanks to decoration. Okay, just a summary. So a decorator takes a function as an argument and returns a modified version of that function. And then once you have that, you can use the add decorator syntax as a simple shortcut for applying the decorator to your function. Yeah?
I've seen that some decorators take arguments.
Yeah.
How do you work that in the system?
Yeah. Okay, so I guess I'm running out of time. But I guess it's nice to mention also that you can parameterize the decorator. So you can actually pass arguments here as well. Yeah. So, yeah.
How do you declare the decorator as a function? It takes more than just a function as argument.
Yeah. I'll show this. I guess it's best if you come to me after the lecture. Okay. But it's essentially in the decorator definition. You just, I think you essentially add arguments here, but I'm not entirely sure. We have to look it up. Okay. Yeah. Okay. Thanks. See you next week.